So welcome everyone again, and today we're extremely happy to have Pasquale Calabrese as our speaker. And well, you all know him, so it's always a bit tricky to do an introduction for someone that you actually know very well. So I just remind you a couple of things that Pasquale studied in Pisa, where he got his PhD, and from there he moved first to Oxford and then to Amsterdam. And finally, he came back to Italy as a professor, first in Pisa and then at SISSA, where he's been since 2014. And well, as we all know, he's a world expert in the physics of low-dimensional quantum system. And in particular, he's most definitely the world expert about entanglement for this kind of system. And today he's going to tell us why this matters. Please, Pasquale.
Thank you, first of all, for the invitation and then for the kind introduction. I'm really happy to be here, also because I can reach people in many different fields, and I will try to tell things that can interest everyone from condensed matter to string theorist. Let's see if I manage. Okay. So what? Maybe you heard already that according to many people, we are living in what they call the second quantum revolution. There have been written books, popular books also. This is one of them. There are many that, as you can read, from entanglement to quantum computing and other super technology. Honestly, this second quantum revolution, it's not my favorite word to describe the era we are living nowadays. Probably it's more appropriate to say, using the term invented by John Preskill, that we are in a noisy intermediate scale quantum era. And basically in this era, what we have is that we have some quantum computers, but they are not yet really good objects. They are small, in this sense, intermediate scale. Okay, they have just about 50 to 100 qubits. And they are noisy. That's the worst thing. So there is not the coherence that is necessary to get, as it's saying in jargon, a full tolerant quantum computer. When we will have full tolerant quantum computer, I don't know. According to the optimistic people, 10 years will be enough. I'm really skeptical on this time scale. But okay, maybe some of us, the youngest people in the audience, they will surely see the quantum computer. However, this talk is not about quantum technology. Okay, I will not discuss at all this part of the revolution, which is the industrial one, and I will mainly focus on the fundamental part of the theory that within many years brought us also to this technologically advance that would have been impossible without some pioneer people that in the 80s, 90s were thinking seriously theoretical on these things. And nowadays we are not yet there, but definitely we are much closer than we were already 10 years ago. Okay, so what I will talk about? I will talk about entanglement, but what is this entanglement? Okay, I don't have to define the entanglement. You know very well that because of superposition principle, this state is entangled, and I should not say why. But what entanglement brings? What does it mean that there is entanglement? And this will depend to whom you ask and also when. For many years, like let's say from the 30s up to the 70s, it was mainly considered a spooky action at distance, as Einstein said first. And okay, because at that time, people were wondering why we have entanglement, how it's possible that we have entanglement, etc. This is a question that is still there. It's not it's a very relevant question. But like in the 80s, 90s, many people, the founder of quantum information, change question. Okay, what we can do with this entanglement? Let's forget about just for a while why is there and how really can be compatible with other law of nature, but let's try to use it, what we can do. And in these years, entanglement became a resource for quantum computation. and for quantum technology in general, so for communication, communication, computation, information in general. Okay, but this is what happened basically in the 80s and 90s, where actually a relatively small number of people really make big breakthrough in this field. But then later, in around 2000, which is more or less when I start being interested in the subject, entanglement became also a tool to study and characterize its phases of matter. In particular, there was a lot, there was and there is still a lot of emphasis about new phases of matter that can be understood thanks to entanglement, and I will talk explicitly about that also. But even later, like just in the last 10 years or so, entanglement became a key to understand the fundamental laws of nature, and I will try to motivate also why this is the case. Obviously, when it's not that what happened in 2010 cancel what there was before. Okay, these are all things that some add up. Entanglement is still a spooky action distance for in some sense, it's still a resource and it's still a tool and it's also a key. So it's just a new thing that the entanglement became. It's not it's not substituting the previous one. But one of the main idea that brought to this increasing interest in entanglement was to pass from few body entanglement to many body. Okay, for many years, from 30 to 80s and 90s probably, theory and experiment were focusing really on few qubits, few objects, few photons in these plots here that you can see in Wikipedia that are entangled for some reason and try to explain what it does, why, and what we can do with them. Okay, quantum teleportation nowadays is mainly based on few photons that are, or other objects that are teleported. Instead, what happened around the year 2000 is that people start wondering, is there something new that we can extract from the fact that many body systems are entangled? Okay, and here I report just one cartoon from an experimental paper a few years ago. And this subject that started theoretically as basically all the subjects in the last 20 years, let's say, it became, and is still, a very active experimental field, as I will try to motivate in the following. But the idea that came from entanglement really spanned completely different fields, from cold atoms to string theory and black hole entropy, as I will, that is one of the things I will discuss, and really enter into popular culture also. I report here, just for curiosity, 2 pages of an Italian comics that is called Martin Mister, where in these comics, the main character, that is this guy, is talking about something that is known nowadays as ER equal EPR conjecture, that was pointed by Maldacena and Sansky. This is a paper of 2013. And okay, what actually saying is not, from Wikipedia, you can read that what Maldacena and Sansky did was to connect the famous EPR pair with the wormhole in, not wormhole, the Einstein-Rosen bridge in general relativity, okay? And in these comics, it was just used to explain some crazy things about space travel, but it's not what the comics does. But the fact that this idea that was out to physicists in 2013, in 2020 was already in a comics, I found quite remarkable. Okay, it's usually before something is understood by in the popular culture by people that are not much interested in science, take ages and ages. Instead, this concept was soon used, at least in these Italian comics, maybe in other even before, I don't know. And surely they had very good scientific consultants to have this idea. Okay, but going on, what is the goal of my talk then? I will try to show many apparently unrelated results in disparate fields of physics that have as common denominator many body entanglement. Probably there are too many results, and I will not discuss all of the one that I prepared in the slide, but okay, let's see where we go when we arrive. And the main goal is to convey the message that many body entanglement brought new and fresh ideas for a deeper understanding of nature in many different fields, from high energy to cold atomic system. Here you see that this is a statistics made by the Heat from Qubit collaboration, where they were showing the number of FTH preprint with the word entanglement in the title, which passed to 0 or few units in the beginning of 2000 to 220 just in 2015, and this curve is still growing. Okay, and okay, so this to show the interest in high energy physics. For cold atoms, this cartoon here represents how a typical experiment on randomized measure, that is one of the techniques that is used in, especially in ion traps experiment, works. And okay, I will not discuss how it works. I will just show some result on this experiment. By the way, for everybody, just feel free to interrupt me if you have questions, and okay, I will try to answer. I don't know if I will answer all. So the first question talking about entanglement is how we can quantify the entanglement. How can we quantify the entanglement? I see a raised hand, please. Go on.
Can you hear me?
Yes.
When you say many body, but you're doing tensor products of 2, does that not involve tensor products of many?
Where I'm making tensor products of 2.
Well, in all of your equations, you have tensor products of 2.
No, this was, here I had tensor product of 2, which is in the column few body entanglement.
And on
here,
the right also?
What?
On the
this
right
is
also?
that some A and B are composed of many particles.
Yes, yes, but you're only taking tensor product of 2 Hilbert spaces at a
time. I'm discussing many bipartite entanglement of many body system.
So you don't require a tensor product, a multiple tensor product.
It can be, this object can be each subsystem Hilbert space can be done of billions of particles, even infinite. For actually, will be infinite in most of my talks.
No, I'm asking how many factors there are in the tensor product. Is it only 2 or is it n?
It depends on what you mean. Inside each of these Hilbert spaces here, there are as many as you want constituents.
So you do not have HA tensor HB tensor HC?
Yes, HA is done of H1 times H2 times H3 times H4 times H5 times however H you wants. But I will not ask, at least for the first part of the talk, if what is the entanglement between all possible constituents in multipartite setting. I will just focus on what is known about bipartite entanglement. That's what is written here in red. The fact that the system is many-body, okay, so it has n or infinite macroscopic constituent. So the Hilbert space, the total Hilbert space is the product of n independent spaces. Doesn't mean that I cannot divide in just 2 parts.
Okay, okay. So the HA itself could be a tensor product of something smaller.
HA itself is a tensor product of something else, and HB is a tensor product of something else.
Okay, thank you.
Okay, so let's go to the definition that probably would have clarified even this point. So we consider a pure state psi, which is an object in an Hilbert space, which is whatever dimension, 2 to the n if we are talking about qubits, or in field theory is not even well defined what is the dimension. The density matrix in a pure state is just the projector. Now, what we do is to consider 2 parts of this many-body system, okay? And in these 2 parts, there are 2 Hilbert spaces, which we call HA and HB. Each of them, as I was telling, is done of many microscopic constituents. Okay, and usually, if the state is entangled between H, A, and B, the state psi will not be a tensor product of the two. Then the reduced density matrix of the subsystem A, of the part A of the system, can be defined as the trace over the degrees of freedom belonging to the Hilbert space B of the density matrix of the entire system. Since the state initially is not a product state, this reduced density matrix corresponds to a mixed state, and it has a non-zero von Neumann entropy, okay, which is defined as usual as the minus trace of rho A log rho A. The von Neumann entropy of the reduced density matrix is known as entanglement entropy and measures the bipartite entanglement between A and B, independently of how big are the two Hilbert spaces, how many constituents they have, what the constituents are, if they are boson, if they are fermion, if there are anyons, or any other crazy particle someone would invent in the future. This is always well defined. And okay. By the way, in the future, in this talk, I will just consider the two parts of the system corresponding to a spatial bipartition between in the system. So a bipartition in space. I will not make other kind of entanglement measure that also exist, but they will bring me far from what I want. Okay, so this is the definition. The entanglement entropy is known to be a good entanglement measure in quantum information sense, and I don't want to motivate it here. And I will just say this is a good measure of entanglement, and let's see what we can do with it. First of all, we should understand how we can access this entanglement entropy in a many-body system. Okay, the possibility one is to use a quantum computer, either analog or digital. But okay, as I said at the beginning, we don't have yet quantum computers, so we should find another way. Why we need a quantum computer? Imagine that you have a many-body system like formed of n spins here. A generic state will be a superposition of the element of the basis, which are 2 to the n for a spin or a qubit, where n is the number of particles. And so you need to specify 2 to the n coefficient to understand, to define the state. Okay, so first of all, calculating this state, if it's not given by something, will be extremely complicated because you have to compute 2 to the n factor, which in practice, on the most powerful computer on the earth, you can arrive to 40, not much more than that, in some very specific simple cases. So 40 is quite far from a really many-body system. And okay, only in some specific case. But even if you have this coefficient by some very nice techniques, for example, Bethe ansatz, for who knows what they are, you still have to construct the reduced density matrix, so you have to trace some degrees of freedom. And also, these operations are exponentially difficult in the number of degrees of freedom. Okay, so it's basically impossible to handle in a decent way, brute force, this object on a classical computer. So the possibility two that we have at hand is to develop appropriate theoretical and numerical frameworks that allow us to describe these many-body states and allow us to compute the entanglement. One of the methods that I want to discuss, that I think is nowadays at the core of all calculation of entanglement entropy, basically, is the Replica approach, which was a framework that basically we introduced together with John Cardy in 2004, and obviously was based on previous work, not that we took out it from the head. But still, the framework itself, I believe, was the most important result that we provided in that paper, not the many physical results that also you can find, but really the framework, which I think was inspiration, as you will see, for many other things that happen after. So the entanglement entropy, as we said, is just the von Neumann entropy of the reduced density matrix. how we can compute it. Okay, our first basic idea was computing this object is difficult because if I want to compute the logarithm of a matrix, I need first to diagonalize it, so which is an expensive operation. Okay, and then I could calculate this functional of the entropy. But instead, what we can do in a much easier fashion is the product of matrix. So why not computing trace of rho a to the n with n being an integer number, okay, which just makes row by column products of matrices, and so study this quantity first of all, and then try to extract from this quantity entanglement entropy. How to do that? This we can borrow a trick from a random system, from the replica trick of random system, where we can just say we can take we should make an analytic continuation in this n from integer number to complex one, then make the derivative with respect to n and send n to 1. Okay, so don't forget a minus sign, but this is easy. Notice that we send n to 1 and not to 0 like a random system because in the expression of the entanglement entropy there is this factor rho a here that sent to 1 and not to 0. But then, okay, so this is a trick. Clearly, it was more or less in the air. But what is trace of rho a to the n? Okay, one nice thing is that for any integer, the trace of rho a to the n in the ground state of a many-body system can be obtained by sewing together n-cut plane, as done in this plot here, resulting in a partition function on what is known as an n-sheeted Riemann surface, okay, which is a basic object of complex analysis. Why is that? Okay, each of these planes represent in Euclidean space-time one of the density matrix rho a. So we pair few of them, 3 of them here, okay, and then to make the product row by column of each of 2 of these matrices, what we should do, we should identify the element on the one side of the cut of the plane with the element on the other side, because this cut here represents the indices of the matrix in an Euclidean path integral. Okay, so all in all, our desired object, trace of rho a to the n, is mapped to a partition function, which is something that is computable in field theory in much easier fashion than diagonalizing the matrix. I see again a raised hand, please.
Sorry, it's me again. What do the endpoints of the cut mean?
The end point, this is
The branch point.
This is a path. This is a Euclidean path integral. Each of these sheets represent the reduced density matrix, okay? And the cut is along the subsystem A of the system that you see here, okay? And the 2 sides of the cut, as in all path integral, represent basically the row and the column of the operator in question.
But is the cut a finite segment in the
in this
plane?
plot is a finite segment, can be whatever, can be 3 separate finite segment, can be it's not important what it is. Obviously it changed computationally, but for what concerns this slide and most of the talk, it's whatever is the subsystem A of interest, you can build this object.
So is there a physical significance to the endpoints?
The endpoints are the separation between A and B. This is the subsystem A, and the rest of the system is B. So the endpoints are the area separating A and B, which is a fundamental object in what will come. So this is the reduced density matrix of the subsystem A, okay, as a path integral. I just skipped some details because I thought I will not give time to give too many details on that. But I see other raised hands. So.
Yes, hello.
Yes.
Hi, I've always wanted to ask an expert like you this question. So I understand you can compute this trace row A to the n for arbitrary integers using this path integral on this n-shaded Riemann surface. How do you choose, though, the analytic continuation to n equals 1? How do you, because there's many of those, so how do you know which one?
Yeah, there is a theorem due to Carlson that goes back to 1913 that probably you know it. If you
Yeah, no, I'm aware of this. I'm aware of, yeah. Anyway.
Yeah, this theorem says that the continuation is unique once you fix some proper condition at infinity. Okay, and this is a very important point. In some cases, it's really easy to understand what is the only possible analytic continuation, but in some cases it's very hard, and you should impose basically that there are no essential singularity at the infinity. That's the main message. Yes, you should.
To me, it always seems kind of ad hoc that you require some behavior at complex infinity on this function that it's exponentially bounded, and so on, whatever goes into Carlson's theorem. But you're saying that has some, that has some relevance.
But because you should think that what you are doing, you are summing the eigenvalues of a reduced density matrix or a density matrix, then that are all smaller than 1, and okay, so they should uniformly converge to an analytic function. Okay, you can really there are some places in the literature where the requirement to put at infinity have been really discussed in a lot of details.
Okay, thank you.
And by the way, things are much more under control than what happened in this older system, exactly from the fact because this object comes from the sum of eigenvalues that are smaller than 1, which is not the case in this older system. Okay, so this is where, in fact, it took many years to prove replica symmetric breaking solution of Parisi, but here the situation is much easier, and there is basically very little to prove. It's discussed in a few papers. I can suggest, for example, one of Cardicas related to ion, where this issue is discussed in a specific case in a lot of details, but there are also other papers where this is discussed. Okay. But this is a very good question.
Thanks a lot.
Okay. So, if I remember well where I was, trace of rho to the n is equivalent to a partition function. And calculating partition function is something that we know how to do in field theory, okay, and where many results can be borrowed from the past also. So we are really, this changed the way we can compute this, the entanglement entropy in a deep way. And not only, what we pointed out in this paper of 2004 is that not only this is a partition function, but this partition function can be interpreted as a 2-point function of some object which are called twist field. And for the expert, please, if you don't understand what I'm saying, don't be afraid. I will not use this concept. I will not, if not only mention. Twist fields are primary field in the orbifold theory that you can get from the replicated theory with Zn, and were introduced in conformal field theory and string theory back in the 80s for completely different reasons, okay? If I can say, one of our results was to understand what these twist fields are useful for in the computation of entanglement entropy. We didn't invent them. They were already there. Probably the first one that nominated twist field was Knitzing, but I'm not even sure of that. Okay, so this replica approach to the entanglement entropy, as you see, makes connection between several different things that brought to many results that I want to emphasize the breadth just now. Okay, first of all, what we can say about this replica. Okay, what are the results that we can derive in this way that actually the main one probably were derived even before. And I want to focus on the entanglement in the ground state of physical system. So let's now consider the case in which psi is the ground state of a local gap Hamiltonian. For high energy people, I mean, psi is the vacuum of a massive quantum field theory. It's the same thing. Okay, what was known, was pointed out, and then sort of proved in some circumstances, is the concept of area law. Area law means that the entanglement entropy for large subsystem is proportional to the area which separates A and B. Like in this plot, is proportional to the perimeter of this surface here, A. Okay, so this is the area law that obviously resembled the black hole entropy, and in fact, it was introduced exactly to explain the black hole entropy. But one of the main results is that this is true for a local gap Hamiltonian, so for a massive quantum field theory. What happens when theory is massless, or our condensed matter theory is gapless? The question was asked maybe for the first time by Olsen, Larsen, and Wilczek in '94, where they considered a 1+1 dimensional conformal field theory, which is the simplest example probably of a gapless theory or a massless field theory. And what they considered was the entanglement of an interval of length L embedded in an infinite system, okay, on the infinite line. We are in one spatial and one time direction. What they found out that the entanglement entropy is proportional to the logarithm of this L of subsystem A. Okay, so it doesn't satisfy the area law because the area of this subsystem will be just Q. It's a number. So the entanglement entropy should saturate to a number in the case of a gap, of a massive field theory. And the coefficient that is in front of this logarithm is 1/3 of the central charge of the conformal field theory. Okay, and this was a fundamental result also because became with time one of probably the most effective way to determine the central charge in one of these systems. But then, why this is important? Okay, one first application that was taught at the beginning of 2000, okay, is realizing that if we have a big Hilbert space, a generic Hilbert space of a many-body system, the entropy of a random state or a state taken at random in this Hilbert space will be extensive, will not be area law, will not be logarithmic. That is a very small variation on the area law. So only a tiny fraction of states satisfy the area law. Actually, people prove that a measure 0 as the Hilbert space has measured 0 in the full Hilbert space. Okay, so it's very little state. Then the idea that came to many people working in the subject was that if we can limit the search for the ground state, not to the entire Hilbert space and then you running, for example, a variational approach in this huge space, but if we can limit only in some way to the area law state, we will be able to determine, to reduce the complexity of the problem in a extremely major fashion. In one dimension, you will get a finite number, okay, not from 2 to the n to a finite number, which is the entanglement of the small system, of the subsystem that satisfy the area law. And in fact, one meaning of the entanglement entropy from a computational perspective is that it gives the minimal amount of classical information required to specify psi. So, okay, the 2 to the n complexity we were talking about was an upper limit for all the states, but for each state, the complexity of the state, the number of coefficients you need to know is the exponential of the entanglement entropy. And so if you can work in this subspace with small entanglement entropy, will be much easier. And to do so, people introduce the concept of tensor network state, okay, which is a powerful set of numerical methods which are based on the entanglement content of this quantum state. And we have many of them nowadays. There are the first one are matrix probable states, which works extremely well in 1D and was even unclear why they were working in one dimension. It was understood only thanks to the entanglement. But then based on the entanglement content of some state, for example, for critical state have been devised MERA. But in order to reproduce, for example, the area law in 2D, some object called the PEPs, which means project entanglement pair states, have been introduced, and they work satisfactorily well in 2 dimensions. Nowadays, to use the word of Subir, such that we have an alphabet soup of proposal for making this tensor network state, each that work in the situation for which it has been designed, but they manage, thanks to them, we managed to handle problem for which a few years ago we thought only quantum computer can really give the answer. Okay, and there are people working, for example, also on simulation of lattice gauge theories via this method, and I think this is a very promising direction that I will not discuss here. But okay, the replica also, I think, brought many ideas also to the experiment. For example, the first experiment in which an entanglement entropy was measured was this paper by the group of Marcus Greiner in Harvard, where they measured actually not the entanglement entropy, the von Neumann entropy, but they measured the Rényi entropy with just a I forgot a logarithm here. There is a log missing here, and are just the logarithm of the moments that I introduced before for integer n. And what they did, they measured for cube, even if it's possible to measure for 3 and small integer, it's possible. And the way this first experiment worked was exactly to produce 2 copies of the state, as it's explained in this caption of the figure here, then to make some proper interference to build from these 2 copies the second Rényi entropy. Okay, and this is very much inspired, obviously, to the idea of replica we just explained in conformal field theory. And in this experiment, you can see, although it was the first one and was done for very small system, but you can see some of the features that I've been discussing, like what they studied was a system that has a transition from a gapped phase called Mott insulator to a gapless phase called superfluid. And you see that the entanglement entropy in the Mott insulator phase doesn't depend on the bipartition because there is the area law, but as you enter this superfluid phase, the subsystem, and in particular the length of the subsystem, matter. And if you analyze in more details, you can find some of the signature of conformal field theory in spite of being very small. It's not log L, but there is the corresponding finite size formula, but it's not important. What is this exact formula? But okay, the entanglement entropy also brought a lot of effort in the high energy physics context, especially in the holographic, in the SCFT correspondence. Okay, just a few words about the SCFT correspondence. This is just a theory that says if you have a quantum field theory living in a D+1 dimensional space, this is a dual in a theory of gravity, which lives in 1 dimension more, okay? So in D+2 dimension. And Ryo Takayanagi in 2006 proposed a formula that nowadays is extremely famous, which connects the entanglement entropy of a bipartition in the boundary theory, in the boundary conformal field theory of quantum field theory, to some quantity in this bulk space, which is ADS space, and their conjecture is that the entanglement entropy is proportional to the area of the minimal surface in this ADS background that you can construct that has A as boundary, okay, as is in this plot. Since the space is carved, for the non-expert, the minimal surface area is not just the volume of this area here, as will be in flat space, but it's something else which actually correspond, and they made explicit computation also in 1+1 dimension, for example, to show that corresponds to the famous result C/3 log L. Okay, and yes, this Gn is the Newton constant if you are curious about it. But this idea sparkled very important concepts. For example, there is this famous paper by Mark van Ramsdorff, in which he proposed the idea of building up the space-time starting from the quantum entanglement, okay? And as he was arguing, the space-time naturally emerge in any theory of quantum gravity as the entanglement between the constituents, okay? And okay, then he discussed much more about this, and there have been a lot of efforts to understand this idea of emerging space-time from the entanglement, but it's not, was again to give an idea of what has been done. What I can discuss a bit more is the very recent idea about black hole information paradox and the page curve. What is the black hole information paradox? As you know, a black hole emits radiation, and this was argued by Hawking, okay? And so in emitting this radiation, the black hole will finally evaporate. As the black hole evaporates, the radiation that it emits is entangled with black hole interior. What does it mean that it's entangled with the black hole interior? That it has a growing entropy, okay, as the time goes on. And Hawking calculated semi-classically the entropy of this evaporating black hole, and what he found was that the entropy was always growing linearly in time. Okay, so his result was the entanglement entropy was growing linearly. But this result is a complete paradox for many reasons, because, okay, at the end of the day, the black hole will fully evaporate and there will be nothing for this radiation to be entangled with, okay? So there cannot be a non-zero entropy in this system because there is not an interior of the black hole anymore. Okay, and this paradox was understood very soon that that was not possible. In fact, it's also incompatible with unitarity of this theory. And in the years, many ideas were proposed, and obviously the basic one is that at some point, for some reason to be understood, as was pointed out probably by Page as first, is that the particles that previously were entangled and were inside the black hole at some point start being emitted, and this would correspond to a reduction of the entropy from some point onward. Okay, and Page suggested this famous curve, which is more or less almost a triangle to explain the real behavior of the entropy of the black hole during this evaporation process. But how this can be formulated? A very nice idea that was proposed in 2019 by 2 different groups was that of the replica wormholes, okay? Which I like because it's really connected to this concept of replica that I was explaining before. And what does it mean is explained very well just in the abstract of this paper that I will read just for you, that the large discrepancy between the von Neumann entropy as calculated by Hawking and the requirement of unitarity is fixed in this paper by including new saddle points in the gravitational path integral. Okay, these saddle points were not seen by Hawking. Why? Because the saddle arise in the replica method as complexified wormholes connecting different copies of the black hole. So basically, there are some saddle points that were invisible to Hawking because he was not using the replica to calculate the entanglement. And which instead, using the replica trick, you can see these kinds of saddle points, which are the wormholes between different replicas. And the most important one is the fully symmetric one that is depicted here, that actually gives a decreasing contribution to the black hole entropy, and explain actually in a quite general fashion, because then in both papers there are some examples in which these kinds of idea works, but the idea is very general. It's not limited to the specific case that one can consider, and probably will be true for any possible theory of quantum gravity. Although this is not my main experience, so I will not really, I'm not able to answer a difficult question on the subject, let's say. Okay, so I will now move to something completely different, and which will likely be one of the last topic, which is another extremely important application of the entanglement entropy, which is in topology. As you know, a topological system, a topological phase of matter is a phase for which you cannot identify a local order parameter in the Landau sense. Okay, and what Kitaev, Pasquale, and Levin and Wen pointed out in these two papers in 2006 is that the entanglement entropy, in particular topological contribution to entanglement entropy, is a non-local order parameter for these topological phases. What is the topological entanglement entropy? Okay, the entanglement entropy, for example, of a two-dimensional system satisfies the area law, and so it's proportional to the perimeter of the system. But then there is a subleading contribution gamma, and what these people point out that this gamma, this contribution, first of all, is negative. Okay, something that is not at all true for non-topological system, and it depends on the topological phases in which the system is. Okay, and distinguish the various topological phases. For example, as written in Wikipedia, the simplest fractional quantum mode state, the laughing state, at filling function of 1 over m, has topological entanglement entropy, which is equal to 1/2 log m. Okay, other very important topological state like ZU fractionalized state, ZU spin liquid, quantum dimer model, Kitaev story code, which is probably the most famous one, gives as a topological entanglement which is equal to log Q. Not only
excuse me?
Yes?
I'm wondering, here this topological entanglement entropy only works for the ground state of this.
Yeah, I'm talking about the ground state. Sorry,
okay, thank you.
And actually, maybe to someone can even think to write in the Wikipedia since it's not written. But okay, apart from that, Kitaev and Pasquale and Levin and Wen also identified some bipartition in which you can make the combination of the entanglement of different bipartition in such a way to erase completely the unwanted area term and just being left with the topological entropy. For example, in this cartoon here by Levin and Wen, you see that if you take this A1, you subtract A2, you subtract A3, and then you add A4, and you make this combination of the entropy, the perimeter will sum up with this sign to 0, and so this object goes to 0. But here you have one topological term, here you have one, here you have one, and here you have two because these two guys are disconnected. And so in the end, by making this operation, you completely erase the perimeter term, and you are left just with 1 minus gamma, which gives directly, without making any fit, apart subleading correction, should give the topological entanglement entropy, which is, as I said, a topological, an order parameter for this topological phase. But an even more amazing breakthrough in this field came from the work of Lee and Haldane of 2008, which is the relation between topological order and the entanglement spectrum. What Lee and Haldane noticed is that, okay, first of all, they write rho as e to the minus h, where h is some object called entanglement Hamiltonian or modular Hamiltonian in field theory. But this, what they pointed out, as written in the text of the paper, is that we point out that the spectrum of this entanglement Hamiltonian, which they call the entanglement spectrum, reveals much more complete information than the entanglement entropy about this topological state. Why? Let's see the results for the laughing state I was talking before, and a real system of electron coupled in such a way that there should be in the same topological phase as the laughing state. That's what people believe, that these two objects are in the same topological phase. And in fact, if you compute the topological entropy, you get, but it's hard, and you get something that is compatible with the same. But what Lee and Haldane pointed out, that just by looking at this spectrum and focusing on the low part of this entanglement spectrum, which means the largest eigenvalues of the reduced density matrix, because here there is a minus, so the lowest eigenvalue of the entanglement Hamiltonian, which are the largest of the reduced density matrix, you can find signature of topological physics in the degeneration of the states, which here you see it's 1, 1, 2, 3, 5, which is the same that appear here. And you see all this low part of the spectrum is identical here and here, okay? And this low part of the spectrum is what characterizes the presence of a topological order. In this model, which is a real model of electron, there are many other things that are high up in the spectrum, which don't matter for the topological order. And actually, when you increase too much the interaction and you destroy topological order, what happens is that all this mess that is up here goes down and destroy this nice order that is down here in the topological order. And by the way, the degeneracy of the states that are reported here are connected to the modular properties of the CFT that lives at the edge of this quantum Hall state. So it really matches very different objects in a nice and powerful way, which really revolutionized, especially the field of quantum Hall physics, but of topological order in general. Nowadays, if people that study quantum Hall spectroscopy and these kind of things, they just, it's a huge specialization just to understand the entanglement spectrum of the system. And it was a real revolution in the field. Okay, how much time do I have? I have 5 minutes left.
5 minutes, yeah.
Yeah, I would prefer to stay in time and leave time for questions. So probably, yeah, I think I want to give this as last example because it's something to which I contribute. Particularly is that the connection between entanglement and thermodynamics in the non-equilibrium system. Okay, so imagine that we have a non-equilibrium system like the, actually like the black hole of before, which is prepared in a many-body state, psi 0, which is not an eigenstate, and that we let it evolve unitarily. Now, the reduced density matrix depends on time. In this case, it's not anymore a constant object like in ground state, and it has a time-dependent entanglement entropy. In the field of non-equilibrium quantum system, we say that a stationary state exists if the reduced density matrix has a limit, okay? And usually it's said that the system thermalizes, because, okay, the entire system can never thermalize, the time evolution is unitary, but subsystem can thermalize if the reduced density matrix of the subsystem, constructed always by taking the reduced density matrix of the thermal ensemble, is equal to this, to the reduced density matrix of the subsystem at infinite time. Okay, so if any local subsystem finite for large time attain a stationary value which is the same as the reduced density matrix of a thermal state, then the system is thermalized. Okay, so this is the definition of thermalization. But this definition tell us, in particular, that the entanglement of the thermal subsystem is equal to the entanglement of the subsystem at infinite time. But since the thermodynamic entropy is extensive, which means that the density of entropy, the ratio between the thermodynamic entropy and the volume of the entire system, should be, apart from boundary effect, equal to the ratio between the entanglement entropy of a large subsystem divided by its own volume, we have that the thermodynamic entropy of the entire system, of the thermal entropy of the entire system, is equal to the entanglement entropy at infinite time. But so we arrive to the conclusion that for large time, the entanglement entropy becomes the thermodynamic entropy. Or if you see this same equation vice versa, that the entropy of the stationary state is nothing but the entanglement that has been accumulating during time between any subsystem and the remaining part of the system. Okay, and this is a really quite nice idea that in fact has been also seen in experiment. This is, for example, the first experiment discussing these ideas, which the title is talks by itself, quantum thermalization through entanglement in an isolated many-body system. What in this experiment did was exactly to do this, focus on a subsystem, calculating the subsystem entropy, and showing that this, in fact, is equivalent to what you would expect from thermal entropy. And I believe that, okay, this is a paradigm shift about the origin of the entropy, okay, which, by the way, has no counterpart in classical system. Okay, so entropy is well defined in classical system, obviously, but the origin of entropy in quantum system is strictly intertwined with entanglement, and this is very important. Okay, let's to show some example of how this entropy first grow and then saturate. This system in this experiment were very small, that's why you see this finite size effect. But later on, there is another experiment, for example, this one by the group in Innsbruck, where they probe ray entanglement entropy via randomized measurement. And they, in this ion traps experiment, they were able to study much larger system, as you see here in this plot, like up to 15, but even up to 20. And you see that as time goes on, you see this linear increase followed by saturation, which is a characteristic trait of the entanglement. I don't want to, okay, I just want to say that we can understand this linear increase followed by entanglement by two different mechanisms that applies to integrable system and to chaotic system respectively, and they are known as quasi-particle picture and membrane picture. And they both predict linear increase followed by saturation for a compact subsystem, but they give different results when applied to more complicated subsystem, which lead to the idea of scrabbling of quantum information, which is something that I cannot discuss. So I will skip many of the other slides that I prepared, and sorry for that. And okay, not only the slide that I prepared, I skipped, that were about the mixed state entanglement, which I skipped, because up to that point, I just talked about pure state, but there are mixed state in nature and we should study them also. And the other was about a very interesting topic, recent topic, that is measurement-induced phase transition. But also, like, I didn't discuss the importance of entanglement in disordered system many-body localization. I didn't discuss the connection between entanglement Hamiltonian and algebraic quantum field theory, which I can remind a very nice review by Witten on the subject. I didn't discuss the entanglement in gauge theories, as well as the connection between symmetries and entanglement. Not, for example, from people working on quantum field theory, the new results, new and old results that have been obtained thanks to entanglement entropy, like is known the proof of the C theorem via entanglement entropy by Casini, Huerta, and other people, or the proof of the quantum null energy condition by means of entanglement by Faulkner et al., which is a very fundamental result in quantum field theory. And last but not least, I didn't mention quantum chaos, such the Yeki type model, and many other things. But so the take-home message of this colloquium, which I reported so many different things, is really that when you look at the entanglement deep enough, you get much more information about the system that you are studying, being a black hole or being the Ising model, okay? But that you can get by any other means, okay? And now I will leave time for questions that I hope someone will moderate, and thank you for your attention.
Thank you very much for this extremely interesting talk, for this journey really through the applications of entanglement. And well, I'm sure there's going to be plenty of questions because a lot of things have been said. We can get started with questions. Shaheen, I think you're the first one.
I have three of them.
Shaheen, please.
Okay, thank you for the very nice talk. It was very inspiring, actually. I have a very naive question. You mentioned the relation between entanglement entropy and thermodynamic entropy towards the end. I was wondering whether, in general, this entanglement entropy shows second law of thermodynamics, or whether we have just laws of thermodynamics now. The entropy replaced by the entanglement entropy.
No, okay. The entanglement entropy, like in the ground state of a quantum system, satisfies an area law. So it does not really have a thermodynamic a strict thermodynamic interpretation, because it does not scale with the volume, which is the basic requirement for entropy. Still, the second law of entropy, second law of entanglement of thermodynamics is based about non-equilibrium systems, so the increase of the entropy, and this is exactly what we see in a very different fashion. Okay, it applies when, in those cases in which the entanglement entropy can be understood as a real thermodynamic entropy. But there are variations, okay? Like there is a first law of entanglement which relates the entanglement entropy and the expectation value of the entanglement Hamiltonian. Okay, it's called the first law of entanglement, which is very much inspired to the first law of thermodynamics, and which has it's not the same thing, but it has a similar interpretation. So there are many connections on the lines that you are saying, but they really become the thermodynamic entropy in those cases that I was referring to when the entanglement entropy becomes the thermodynamic entropy. Okay? I hope this answered the question.
And just what about the zeroth law? Is there any notion of temperature, and what could be its
the temperature is, there is notion of temperature, obviously, in this non-equilibrium system. In fact, I was talking about thermalization. Maybe I went to, can you see still the screen or not? Because it went out of.
Yes, yes.
Okay. So here there is the notion of temperature. This system, the subsystem thermalized, and so the entanglement entropy actually fix what is the temperature of your system, okay? According to the ds in the E equal 1 over T. It's a macroeconomical system. It's isolated from everything. But okay, so in this sense, there is a notion of temperature, but in the ground state, it's a zero temperature state, so there is no temperature, obviously. And yes, however, there is instead a connection between the ground state degeneracy and what you can get in the entanglement entropy, which is also related to the Nernst law, to the zero law of thermodynamics. Okay, this required to be specified properly.
Okay, thank you.
Okay, now we have Hartnert.
Yes.
Please.
Can you hear me?
Yes,
yes.
I can.
Okay. You said something in passing about beta ansatz states and integrable systems.
It was mainly a joke. Okay, that in beta ansatz you have a wave function for your states, so you have it, but still you cannot compute the entanglement entropy simply because you have to make an exponential number of operations. And actually, there are very interesting papers written by Rafael Nepomuk and collaborators in which they write some quantum computer algorithm in order to find exactly to do so, to work out the entanglement entropy starting from a beta state. And obviously there are some interesting, for example, the entanglement entropy has been calculated by Smirnov and collaborators up to 9 sites through beta answers, but that's really, and I don't think it will be possible to make more than that.
Well, it's not obvious how to divide it into an A and a B part, but let's say.
No, I'm always, as I was telling in all this talk, I just consider a spatial bipartition. There are other bipartition, but A and B for me are one compact and consecutive spin, let's say. Then we can make
that would be one way, or you could also
that's
have
the
the
most
odd sites and the even sites.
Yeah, but okay, this is called, this object exists, it's called comb entanglement for obvious reason, and it's completely different features. It satisfies a volume law for, just because there are, the area is equal to the volume, and it's an interesting object, but there's a completely different life, let's say.
So the answer is that it is not known for beta eigenstates what the measure of entanglement is.
No, okay, but this is, you can make a different bipartition for any system. The point is, the point of the talk was also how to extract relevant information by making this bipartition, and which has the bipartition that gives most of the information. And okay, the first thing, then you can make more. The first message that I was passing is that taking just a compact subsystem out of a many body system, let's call the black hole geometry, is the one that provide already a lot of information about your system, like topological order that we discussed, information paradox, and many other things that I didn't discuss. And then there are also other information that can be extracted for more complicated bipartition, on which I have been working personally, so I like, but many other people also have been working. And but okay, the simplest one is probably the at first the most informative. Then one can make refined questions to understand even more.
So just to take the simple example of the Heisenberg spin chain, let's say XXX. Is there any result known saying, I don't know, that the beta eigenstate somehow maximize the entanglement entropy if you divide it properly, or anything like that?
No, the beta eigenstate don't maximize anything, unfortunately. But like there are results on beta states, for example. Okay, in the case out of equilibrium, or in the middle of the spectrum, the leading term to the entanglement entropy is given by the Yang-Yang entropy for obvious reason, and this is known by Yang in the 69, not the entanglement entropy, how to compute the Yang-Yang entropy. But if you are interested in this area law, which means ground state or low-lying state entanglement entropy, exact results from beta state are limited to very small subsystems. That's what I say. And the best result, to my knowledge, exact result based on beta states are those by Smirnov and collaborators. But maybe there was something else that I missed. To the best of my knowledge, that's what I know.
Thank you.
Okay, maybe we can go on. Osama?
Hi, yes, thanks for the talk. It was very informative, and I was wondering about when you talked about the theorem where you first mentioned ADS-CFT, and you said that the entropy of a subset A is proportional to the minimum or the minimal surface. Yes, here.
Yes.
Yeah, the area of the minimal surface. Why would there be a minimal area to begin with in the ADS?
Because of the curved space-time. You can easily see that this goes with the volume, very far away it goes with the volume, in the middle should go like differently, and there is a minimum. It's just because the space is carved, it's very obvious that there is a minimum.
I see. So it's also because it's ADS.
It's only because, it's because of the ADS, yes.
Yeah. Yeah. Okay. Thanks.
And obviously, if you had in a flat space, the minima will be just a basic one. In an hyperbolic, you will just go away. And obviously, in a DS, instead, there is a minimal surface because
in DS, it would also be just like a flat. The minimum would be 0. Yeah. Okay.
Pietro?
Hi, thanks again also by my side for the talk. You mentioned the entanglement Hamiltonian, and if I understand correctly, I mean, the entanglement entropy is a function of its eigenvalues, right?
Yes.
So I was actually wondering, like, which are the phenomena or the, I mean, models and problems where the entanglement entropy is not enough somehow to understand the entanglement properties of under exam, and you actually need the whole spectrum or some other quantity which is also a function of the eigenvalues of the Hamiltonian.
I think the most prominent example where the entanglement Hamiltonian gives really a lot more than the entanglement entropy is the topological order. So this example that I brought of Lee and Haldane, okay, you see here that from these kinds of plot, because this is not only the Haldane says this is the spectrum, but he's making a bit more that, okay, I was going fast on this, is not only giving you the number in the spectrum, but is writing to which quantum number they correspond to. So in this object, there is not only information about the value, which is the spectrum of the eigenvalues, but there is information also, there is also some information about the eigenvector, which is encoded in this secondary quantum number of this specific case, which is the Z component of the angular momentum, but it's not important for that. But okay, so here what is probed, although the title of the paper says entanglement spectrum, is really some specific feature of the entanglement Hamiltonian, which indeed, as you see from these plots, lets you understand not only when there is topological order, which kind of topological order, but it's also when the topological order is melt, which was a question that, okay, stayed around as a vague question for since ages. Okay, it was really something that was understood only thanks to, was deeply understood only thanks to this work. Obviously, on case by case side in topological matter, there are results. I don't want that someone misunderstand me. Maybe on the very specific case of laughing wave function, you could do some other indicator that things were going in some way. But then if you change something, you have to change indicator, you have to build up something. Instead, the entanglement spectrum, or better Hamiltonian, gives you, for all topological phases, a very clear signature of what is the topological phase of the system, which I think was really a revolution in the field.
Okay, thanks. But is it also useful, for instance, in random quantum circuits? This fact of the full entanglement spectrum and not only the entanglement entropy?
Probably depends on what you are looking at. Random circuits is something very big, okay? If you want just to study the thermalization induced in random system, for example, that is something like this membrane things I was discussing, I was flashing here. Probably the entanglement entropy is more than enough if you are interested in how the system thermalizes. Okay, but there can be deeper question. For example, this entanglement transition in measurement-induced transition, which is also based on circuits, where for the time being the entanglement entropy, negativity, and also other objects have been studied, but it's likely that the spectrum will lead even more information here. But okay, this is something very recent, as you see from the papers, and people didn't study yet in detail this, but my guess would be that, for example, in this case, the entanglement Hamiltonian could give more information than the simple entropy.
Okay, thanks a lot.
Okay, so we have yet another question. I guess it's the last one since we're starting to get a little bit long. Christoph.
Yes, thank you for the
You are muted, sorry.
We can't hear you well.
Can you hear me better now?
Nope.
Bit better, but not much.
Okay.
Yeah, and I can increase the volume and maybe hear you.
Better now?
Slightly better.
Okay. Okay, so the question is the following. At some point you introduce the complexity, and you related it to entanglement entropy, just a complexity is exponent of entanglement entropy. How unique definition is it?
No, it's sorry if I use the word complexity means everything, and like everything that means everything means nothing. Okay, what I meant by complexity here, which is not the real definition of complexity, or one of the definitions of complexity, is just the what I wrote after, that is the amount of classical information required to specify psi. I meant this about complexity, and which is not a real, it's just a it encodes how difficult it is to put this system on my laptop, and I use the word complexity for this expression, but the real definitions, not even definition of complexity, are much more complicated, and there are several of them, each one with its own specificity for the use you have to do. Okay, so what I meant here was a very basic thing, that is just how much bit I need on this laptop in order to be able to, if I'm smart enough to reconstruct the state, to put it on my laptop. That was the stupid definition that I had in mind.
Okay, because in example of this one-dimensional case, you would just get the length, right? Because
no, I will get, for a gap system, I will just get a finite number. That's the beauty of this MPS, that you need an object that has like 3 or 4 bits. You can encode the entire quantum state if the system has a large enough gap. And then when it's log L, okay, you have to make the exponential of log L with a prefactor will be a power law, so L to the C over 3, and okay, which is a polynomial complexity, okay, which is easily to put also in my laptop. In fact, this matrix protostate works very well. Okay, you just join this small complexity with finite side scaling, and you can extract basically everything about one-dimensional quantum system. Okay. For two-dimensional quantum system, you have to make better, and you need these steps.
Okay, I see. Thank you very much.
But thank you for the question, it was appropriate.
Okay, so I would like to thank once more Pasquale for this extremely interesting and varied analysis of entanglement, and a bit in all the corners of theoretical physics. Is extremely remarkable. So thank you again. And I believe Stefania has something to tell all of us.
Yes, first of all, I will ask Pasquale to send us the slides, and we will publish them. I just answered on the chat to one Amir, who could not attend from the beginning, but the video will be published very soon on the GGI webpage. So Amir, you will enjoy the seminar from the beginning in the next days. I have 2 announcements. The next Tea Breaks seminar colloquium will be on the 22nd of June by Tracy Slater. And then we have a special edition of the Tea Breaks on July 6th, just to say happy birthday to the Higgs boson. And we have 3 talks, one from Replica, who will tell us about all the period for the hunting of the Higgs at CERN from the experimental point of view. And from the theoretical point of view, we have John Ellis, who will tell us how was it at CERN during all the period searching for the Higgs. And we will have an overview for our future, an outlook by Mark Luthi. So I hope you will join us, and we already have advertised this event. Okay, so Pasquale, thank you very much.
Thanks to you.
Not only for the seminar, but also for answering all the questions, and it was very, very great from your side. And have a good evening or what else?
Thanks.
See you.
Thank you again. Thank you
Ciao a
again.
tutti.